Okay, we're now in the orthogonality section, and I'm going to talk a little bit about complex numbers. Now, in this school, we talk mostly about complex numbers in number theory. If you haven't had number theory, this may be new to you, but I'm just going to give you a brief introduction. We're not going to be emphasizing complex numbers very much. Right. But basic idea of complex numbers is that -1 does not have a square root among ordinary numbers that we deal with. There's no real number that squared gives you -1. So what we do is we define this number I to denote the square root of -1. Now this is a symbol. Now there are reasons for doing this, very strong reasons. I'm not going to go into the reasons. I just want you to understand that I represents the square root of -1. So whenever you encounter something like I squared, if you encounter I squared, you can replace that with a -1. Right? And then you get rid of the I. Now, a general complex number can be written as in the form A plus BI. So A plus BI is equal to a complex number. You could think of this as a linear combination of a real number plus some number times I. All right? But we can add these just like you would add them as if they were vectors. 3 plus 4i plus 6 minus 7i. You add the real parts, the 3 and the 6 gives you 9. You add the imaginary parts, the 4 and the -7 gives you -3. So adding complex numbers is very direct. Now, multiplying is a little bit more complicated. You have 3 plus 4i times 6 minus 7i. Now, if you had expression like this using ordinary real numbers or algebraic variables, you would use the distributive law, or sometimes you say the FOIL method. So let's use the FOIL method on this expression. F stands for first. We have 3 times 6, so that's my first term. Then O is outside, 3 times -7i, so that's what I have here. Plus inside, 4i times 6, that's what I have here. And then last is 4i times -7i, that's what I have here. So 3 times 6 is 18, straightforward. 3 times -7i is -21i. 4i times 6 is 24i. We're assuming the I commutes with everything, which it should. Now this last term gives me -28 times I squared. Now remember I said I squared equals -1. So I can replace this with a 28. The 18 plus the 28 gives me a 46 plus 3i. Okay, so that's a way to multiply complex numbers. Now, I recommend when you multiply complex numbers, don't use FOIL, use FLOY. First, last, outside, inside. Now there's a good reason for this. Here, let's do an example here. 2 plus square root of 3i times 3 minus square root of 2i. So let's follow the first, last, outside, inside rule. And what do we get? We'll see how this works. First is 2 times 3, which is 6. Last is square root of 3i times minus square root of 2i. Now, square root of 3 times square root of 2 gives me 6. The minus I squared gives me a -1, which is 1. So I get my real terms, my terms without I, together. The other two terms are going to have an I, so I just separate the I out. And outside is going to be 2 times minus square root of 2i, so that's -2 square roots of 2i. Inside is square root of 3 times 3, which is 3 square roots of 3 times I. And you get this term. Now you could do FLIO also, but FLOY sounds kind of nice. So, brief introduction to addition and multiplication of complex numbers. All right. Let's go to the next one. Okay. Now, You probably saw inner product in physics or some calculus class. In two dimensions, the inner product of two vectors is defined in this way. If one vector is x1, y1, the other vector is x2, y2, then the inner product is defined as x1, x2 plus y1, y2. You can also call this the dot product. Inner product and dot product are the same thing. Okay. Now there's a geometrical interpretation. If you have the two vectors x1, y1, x2, y2, and an angle theta between them, it turns out that the dot product of those two vectors is the length of the first vector times the length of the second vector times the cosine of the angle. Now this is a special case of inner product for Rn. We've done this for two-dimensional vectors. We can also do it for n-dimensional vectors. And furthermore, we can do it not just for real vectors, but we can do it for complex vectors. So if I have two vectors, v, which has n components, v1 through vn, and u has n components, u1 through un, they both have to be the same size, have to have the same number of components. Then the inner product of u and v, which he writes with angle brackets, is written in this way. Angle brackets u and v, and these boldface means it's a vector, means I take the first component of u1, take its complex conjugate, and then multiply by v1. Second component of u, complex conjugate, multiply by v2. Third component, complex conjugate, multiply by v3, and so on. Now, what's the complex conjugate? The complex conjugate of a plus bi is equal to a minus bi. So when you have the I part gets negated. The real part stays the same. The I part gets negated. Again, this may be somewhat unmotivated, but just bear with me right now. Just take that as a definition that the complex conjugate of a complex number is the number with the imaginary part negated. Sorry, it's going screwy on me. Okay, there we go. All right, so here's an example. Here I have u equals 1 plus I, 1 minus I, 1 plus square root of 3i, 1 minus square root of 3i. And v is 1 minus 2i, 2 minus I, 1 minus square root of 3i, 1 plus square root of 3i. Now, what's the inner product of these two vectors? Well, remember, you have to take the complex conjugate of the components of u and multiply by the corresponding components of v. So I'll take the complex conjugate of 1 plus I, which gives me 1 minus I, times the first component of v, which is 1 minus 2i. So this red comes from the first components of u and v. The green comes from the second components. Complex conjugate of 1 minus I is 1 plus I, times 2 minus I. Complex conjugate of 1 plus square root of 3i is 1 minus square root of 3i. And then here I have 1 minus square root of 3i also. So I get this third term from the third components of u and v. And finally, I'm going to get one more term from the fourth components, plus 1 plus square root of 3i here, and then 1 plus square root of 3i there. Now, I could go through and do those complex multiplications, but I thought that would be something good for you to practice on. I should say that although I'm showing you complex vectors, in the class we're going to focus on real vectors, in which case you don't have to worry about the complex conjugates. So let me just do another example. With real vectors, if I say u is equal to 4, 3, 7, minus 1, and then v is equal to minus 2, 1, 5, and minus 7. In this case, the inner product or the inner product is going to be 4 times minus 2 plus 3 times 1 plus 7 times 5 plus minus 1 times minus 7. All right? So, and you can figure that out. So with real numbers, it's much easier. Okay, well, let's now consider another complex vector, w. And let's consider what happens when you take the inner product of W with itself? Okay. So you may have seen inner product written as W dot W. In this book, we're writing it as the angle brackets of WW. And what you need to do, remember, is take the components, complex conjugated, times the components themselves. So this is going to be the complex conjugate of the first component, which is 1 plus I, times the first component, which is 1 minus I, plus the complex conjugate of the second component, which is 1 minus 3I, times the second component, which is 1 plus 3I. Then plus the complex conjugate of the third component, which is 2 plus I, times 2 minus I. And then you have the complex conjugate of the fourth component, which is 4 minus I times 4 plus I. So I'm taking each of these components one by one and taking its complex conjugate multiplied by itself. Now, when you take a complex number multiplied by its complex conjugate, something very interesting happens. Here we have a case here of 1 plus I times 1 minus I, which is my first term here. Now, if we use Floyd, first is 1 times 1, which is 1. Last is I times minus I, which is minus I squared, or 1. Then let's take the outside term. The outside term is 1 times minus I, so I'm going to write that as I and times minus 1. Then inside is 1 times I, that gives me plus 1. All right. So that's going to give me the final result, 2. Now that's a real number. Really nice. So in general, you will get this same kind of phenomenon. If I take A plus BI and its complex conjugate and multiply by A, if I take the conjugate of A plus BI times A plus BI, I'm going to get A minus BI times A plus BI. And you can work it out. You're going to get A squared plus B squared. Now this should look familiar. If I think of the A and B as components of a two-dimensional vector, remember I've been comparing complex numbers to vectors. So if I think of the A and B as components of a two-dimensional vector, then the A squared plus B squared is simply the square of the length of the vector from 0 to A plus BI. Okay. So taking the inner product of a vector with itself has something to do with length. So for any n-component vector, for each component of my vector, I'm going to be getting this squared length value. Now, if the components are real, it's just going to be the squared value. Each one of these components is real and non-negative. So this is defined as the length squared, or norm squared, or length squared of the n-component vector U. Now let's do a real example so you can see that it works also. So let's take U equal to 4932. And then let me take UU. UU is going to be, well, remember, you take the first one times its complex conjugate, but the complex conjugate of a real number is just itself. And here I have 9. 9 times 9 is 9 squared. 3 times 3 is 3 squared. And 2 times 2 is 2 squared. So this is called the norm squared of U. So in other words, the norm of U would be the square root of this quantity. Just like Pythagorean theorem. Okay, you have Pythagorean theorem in 2 dimensions, 3 dimensions. Now we have Pythagorean theorem in any number of dimensions. Right? So we have a norm defined. Norm means length. Our next idea is the notion of orthogonal. A pair of vectors are orthogonal if their inner product is 0. Okay, so let's give an example. Let's talk about real vectors, and here's some three-dimensional vectors: 1, 0, 0, 0, 1, 0, 0, 0, 1. This is called standard basis vectors, and they're usually denoted by E1, E2, and E3. Sometimes they're called standard basis vectors or standard unit vectors. And you can think of these as the three edges of a corner of a room. 1, 0, 0 would be this direction. 0, 1, 0 would be that direction. Imagine that this is the corner of a room. So this would be E1, E2, E3. And they're sticking out, they're perpendicular, and they point in all directions. All right? So what about the inner products between these different e's? Certainly if I take E1 with E1, I'll get 1. E2 with E2 is 1. E3 with E3 is 1. You can work that out. If I take E1 with E2, I'm going to get 0. See? 1 times 0 plus 0 times 1 plus 0 times 0 gives me 0. In fact, if I take any one of these vectors, inner product with any other vector, I'm going to get 0. Right? Geometrically, we know that these vectors are perpendicular. And mathematically, we say that if two vectors have inner product 0, the two vectors are called orthogonal, and geometrically, orthogonal vectors are perpendicular. So here I drew E1, E2, E3, like the corner of a room. E1 is the edge of the floor, E2 is the other edge of the floor, E3 is the two walls meeting together. These are all mutually perpendicular. So we have three orthogonal vectors, three perpendicular vectors, and their inner products are all 0. Now, I'm going to kind of give you a quiz, and of course it's not a graded quiz, but here I'm going to give you two vectors, A and B, and I want you to compute the following inner products. Compute the inner product of A with A, of A with B, of A with 4B, and A with 3A plus B. And then last question, find a real number x such that the inner product of A with XA plus B is equal to 0. So all of these questions use the A and the B above. So pause the video, take a couple minutes to answer this, and then we'll talk about the answers. All right, ready? So here we go. First question was A with A, inner product of A with A. And like we've seen before, you just take the corresponding components and run them down. This gives us the answer 1 times 1 plus 1 times 1 plus minus 1 times minus 1 plus minus 1 times minus 1, which gives me a total of 4. All right? So that's the inner product of A with A. A with B, you do similarly, right? A and B next to each other. 1 times 1 plus 1 times 3 plus minus 1 times 5 plus minus 1 times 7, you get the result of minus 8. Now, this one gets a little more interesting. A with 4B. Here I wrote the components of A, here I wrote the components of 4B. Now notice that each component of 4B has a 4. In fact, I'm going to get 1 times 1 times 4, 1 times 3 times 4, minus 1 times 5 times 4, minus 1 times 7 times 4. Each component is multiplied by 4. So in fact, all I need to do to compute A with 4B is take 4 times the value of A with B, okay, which is minus 32. So in general, we have a property. And the property is the inner product of A with KB is equal to K times the inner product of A with B. Now, when you're dealing with complex, it's the same, but in this case, if you put the K on the first one, you'll find that the result is the complex conjugate of K times A with B. Now, we are not worrying too much about complex numbers, so you can just think that if you take the inner product of two real vectors and you multiply one vector by a scalar, that's just going to multiply the inner product by the same scalar. All right? So that's called a linearity property, and that's one of the concepts in this section. All right, now how about A with 3A plus B? So here I wrote A, and here I wrote 3A plus B. Now, here we have 3's on all of these here. So I could divide this into two parts. I could take the inner product of this with these ones, plus the inner product of these with these ones. And you'll see that I can break this up into two parts. In fact, this is the same as A with 3A plus A with B. Okay, this is kind of a distributive property. So we can write this generally as the inner product of A with, let's see, I can say KB plus LC, where K and L are numbers, is going to be equal to K times the inner product of A with B plus L times the inner product of A with C. Okay. But I think if you think about it this way, you can see how you break things apart and you can extract the scalar multiple to make things easier. All right, so this becomes useful when we want to find the answer to problem 5. The answer to problem 5 was find x so that the inner product of a with xi plus b is equal to 0. So we can write it this way. Now, if I break it apart like I broke it apart before, this first part multiplies by x, and the second part doesn't multiply by anything. So here I get x times the inner product of a with a, which is 4x. And then here I get the inner product of a with b, which is minus 8. And if I set that equal to 0, I get x equal to 2. So again, the important fact is that a with xa plus b is equal to the inner product of a with xa plus the inner product of a with b. And I can pull the x out in the front to get x times the inner product of a with a plus inner product of a with b. All right, let's continue. We've talked about when two vectors are orthogonal, but we can have orthogonal sets of vectors. Now, the set of multiple vectors is orthogonal if every pair of vectors is orthogonal. And I should say every different pair. That's what this means. Vj and Vk, inner product is 0 for all j and k between 1 and n, but j has to be unequal to k. We know that if you take a vector inner product with itself, it has to be a positive number. You can't have a vector perpendicular to itself. That just doesn't happen. So that's what an orthogonal set of vectors is. Now, if the set is orthonormal, there's an additional condition that the set is both orthogonal and the inner product of any vector with itself is equal to 1. So here's an example. I have v1 and v2. Is v1 and v2 orthogonal? In this case, there's only one inner product to check. And if you check that inner product, you get 0, so the answer is yes. Now, is v1 and v2 orthonormal? Well, you need to check the inner product of v1 with itself and the inner product of v2 with itself. So in this case, the answer is no. Because if you take the inner product of v1 with itself, if you scroll up, v1 with itself is going to give you 4. And v2 with itself is also going to give you 4. Now, I can make it orthonormal. How can I do that? Well, let me take this vector u1, which is v1, divided by the square root of v1, v1. Now remember, that's just the norm of v1. So I'm taking v1 divided by the norm of v1. The norm of v1 is the square root of 4, which is 2. So I'm taking v1 divided by 2, and I get this vector. And you can verify that this vector inner product with itself is 1. So in general, to make a vector have norm 1, you just divide by the square root of the inner product of the vector with itself. In other words, you take the vector and divide it by its norm, and it will have norm 1. So that's a way to make it have norm 1. So I can do the same thing with u2. And in this case, you'll also get u2 inner product with itself is equal to 1. Now, since I didn't change the direction of u1 and u2, but only changed the scale, you can verify that u1 and u2 are still orthogonal. All I did was scale them. I didn't change the angle, so they're still orthogonal. So I can take an orthogonal set of vectors and scale each vector and get an orthonormal set of vectors. Our last topic in orthogonality is the Gramschmidt procedure. The Gramschmidt procedure can be used to create a set of orthogonal vectors that has the same span as a given set of vectors. Now, we've seen already that span is a very important concept. And we're going to find that orthogonal vectors are very useful. They have very simple properties. So we're kind of putting those two things together, and we'll see later why it's useful. Now, the basic principle of Gramschmidt is that if u and v are vectors, then this w, defined in this way, is orthogonal to u, and the span of u and v is equal to the span of u and w. All right. I'm going to illustrate this using an example. You can actually work this out and take the inner product of w with u and show that w is orthogonal to u. You can kind of see that because if I take the inner product of w with u, I'm going to get the inner product of u with v here, and then I'm going to get the inner product of u with u here, which cancels this one. So I'm going to get a 0 here. But let's show with a concrete example. Here I'll take u equals 1, 2, minus 3. and v equals 1, 0, 2. Now it's clear that the inner product of u with v is not 0. In fact, it's 1 minus 6 or minus 5. So let's take this vector w that I defined up here. Okay? So I have to take v minus inner product of u with v over inner product of u with u times u. So we just need to figure that out. As I mentioned, inner product of u with v is minus 5. Inner product of u with u is going to be 1 plus 4 plus 9, which is 14. The minus 5 over 14 times u, so here's u here. And then let's just work this out. I have to take the first component of v minus the first component here. So I'm going to put everything over a common denominator 14. So this 1 becomes a 14 over 14. And then the term from this vector becomes a plus 5 over 14 because of the minus here and the minus there. Here I have a 0 over 14, and then here I have going to have a plus 10 over 14 from the second one. Then here I have 2. I'm going to convert that to 14ths. That's 28 over 14. And then I have plus 15 over 4. I'm sorry, it's going to be minus, 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 which is minus 15 over 14. All right, so here I have my w. When you work that out with all the 14s and everything, I get that w is equal to 1 over 14 times 19, 10, and 13. And you can check that, in fact, w is orthogonal to u. Now, I mentioned that the span of uw should be equal to the span of uv. The way to show that two spans are equal is to show that everything in this span is also in this span, and vice versa. So we will show that every element of each set, in each of these two sets, span of uw, span of uv, we're going to show every element in each set is also in the other set. So let's take some arbitrary vector z that's in the span of u and v. What does it mean that z is in the span of u and u and w? Z is in the span of u and w. What does it mean that z is in the span of u and w? It means that z is a linear combination of u and w. So z equals au plus bw. Now, w itself is a linear combination of u and v, according to the expression above here, right? W is a linear combination of u and v. It's v times 1 plus this constant number times u. So we have that. And so I'm just going to replace w with this linear combination. And here I have a part that multiplies v and a part that multiplies u. I'm just going to put all the u stuff together and all the v stuff together. Okay? So in fact, I'm writing z as something times u plus something times v. That means z is a combination, linear combination of u and v. So that means z is also in the span of u and v. I started out with z being in the span of u and w. I showed that z was also in the span of u and v. Now, you can also prove the other direction. The other direction is you start with something in the span of u and v, means that you can write that vector, which I'm calling y, as a constant times u plus a constant times v. Now what you'll have to do is express v in terms of u and w, which you can do. Go to this expression which expresses w in terms of u and v, and solve for v. In fact, all you do is just exchange signs, the w and the v exchange signs, or you can pull this over to the other side. And then you go through the very same proof. You show that v is a linear combination of u and w, and that will make y also a linear combination of u and w. Okay? All right. So, I did that with 2 vectors. You can also use Gramschmidt with 3 vectors. So let's consider how to do this. We're going to start one by one. I'm going to create an orthogonal set W1, W2, W3 with the same span. So I'm going to start out with W1. I'm going to let W1 be equal to V1. I'm going to start with one of these. So it's going to be 1, 0, 1. Now for W2, I'm going to use my W1 and my V2 to get a vector that's orthogonal to W1. Okay? So I'm going to take, and my formula was V2 minus, and let's go up and make sure I got the formula right. Here's the formula here with U and V. but instead of V, I'm using V2. Instead of U, I'm using W. So it's going to be W V2 over WW times W. So down here, I'm going to get W1 V2 over W1 W1 times W1. And these should all have arrows on them. Now, I can show that W2 and W1 are orthogonal. All right, now what am I going to do with the third one? Well, first of all, I'm going to make the third one orthogonal to W1 by doing the same procedure. So I'm going to take W3 is equal to V3. And first of all, I'm going to take off the W1 part. So that's going to be W1 V3 over W1 W1 times W1. But that doesn't make W3 orthogonal to W2. Now, it turns out that all I need to do is apply the Gramschmidt for W1 and the Gramschmidt for W2. And you can show that W3 is orthogonal both to W1 and to W2. Why is it orthogonal to W1? Because this takes out the non-orthogonal part of V3. And then W2 is already orthogonal to W1, so we don't have to worry about that. So why is this orthogonal to W2? Well, for a similar reason, that this takes out the orthogonal part of V3, and W1 is already orthogonal to W2. So you can show that W3, W1 is equal to W3, W2 is equal to 0. All right, now we're not going to do more than 3 vectors. All you need to do is know how to apply this procedure. If you're given 3 vectors, take the first 2, do the orthogonality business. Then once you've done that, you're going to have your W1 is the same as the first vector. W2 is a new vector. Then to get your W3, you're going to take your third vector and do the Gramschmidt business with both of the other 2 vectors. And that's going to get you a vector that's orthogonal to the first 2. All right, so that's it for orthogonality.